What if calculus, the mathematics that powers every satellite in orbit, every bridge you've ever crossed, every prediction your phone makes about tomorrow's weather? What if it was being discovered 2 centuries before Isaac Newton ever put pen to paper? Not in the libraries of Oxford or the salons of Paris, not in Galileo's Italy or Kepler's Germany, but in a small, lush, rain-drenched corner of southern India, along the banks of the Nila River, by a group of scholars so isolated from the Western world that their names were never taught in a single European university. This is not a claim. This is history. And by the end of this video, you will never think about the story of mathematics the same way again. Welcome to Numbers and Narratives by Blesswright, where we go beyond the equations and into the human stories that mathematics is built upon. If you're new here, this channel exists because the greatest ideas in mathematics did not arrive in a vacuum. They were born from real people, real struggles, and real moments of brilliance that history sometimes forgets. Today we're going to explore one of the most astonishing chapters in the history of human thought, the Kerala School of Mathematics and Astronomy, a tradition of mathematical genius that flourished between the 14th and 16th centuries in what is now the Indian state of Kerala, producing results that anticipated the calculus of Newton and Leibniz by over 200 years. If this kind of deep, hidden history resonates with you, consider subscribing. And stay until the very end, because the final revelation in this story is not just mathematical, it is philosophical. It is about how knowledge moves, or fails to move, across the world. To understand what the Kerala school achieved, you first need to feel where they were. Close your eyes for a moment and picture it. The year is 1380. While England is consumed by the aftermath of the Black Death and the papacy is splitting itself in two during the Western Schism, the southwest coast of India is experiencing something almost incomprehensibly different, a long golden age of intellectual cultivation. Kerala, at the southwestern tip of the Indian subcontinent, is a narrow strip of land sandwiched between the Western Ghats, a range of ancient mountains blanketed in dense monsoon forest, and the Arabian Sea. It is a place of extraordinary natural richness, spice groves, rice paddies, rivers winding quietly through coconut palms. The Nila River, known today as the Bharatapuzha, flows through the heart of the region where our story takes place, through a district called Thrissur and further into Malappuram. Along these riverbanks in temple villages called gramams lived a community of Brahmin scholars known as the Nambudiri. These were not idle men. They were deeply trained in the ancient Indian traditions of astronomy and mathematics, traditions that stretch back to the Vedic period, thousands of years earlier. They studied texts called the Aryabhatiya, written by the great 5th century mathematician Aryabhata, and the works of Brahmagupta. Mathematics was not separate from their spiritual lives. For them, it was intertwined with understanding the cosmos, with calculating the precise positions of planets and stars, with maintaining the ritual calendar with accuracy. And it was into this world, this quiet, riverine, intellectually saturated world, that a man named Madhava was born sometime around the year 1340. We know very little about Madhava's personal life. We do not have portraits of him. We do not have diaries or letters in his hand. What we have are texts, mathematical and astronomical works that bear his results, quoted and analyzed by the scholars who came after him. And what those texts reveal is a mind of almost supernatural penetration. Madhava of Sangamagrama. Sangamagrama being an old name for the town now called Irinjalakuda, in what is today Thrissur district, is considered the founder of what historians and mathematicians now call the Kerala School of Mathematics and Astronomy. He was the first, the fountainhead, the man who looked at mathematical problems that had resisted solution for centuries and found, in the concept of the infinite, an entirely new way of thinking. After Madhava, the tradition he founded produced a remarkable succession of scholars, each building on the work of those before them. Parameshvara of Vattaseri, who was Madhava's direct student and a meticulous astronomical observer. Nilakantha Somayaji, one of the most brilliant mathematicians the medieval world ever produced. Jyesthadeva, who wrote the extraordinary text called the Yuktibasa, and Achyuta Pisharati, who extended the tradition well into the 16th century. Together, at over roughly 250 years, these men formed a living intellectual chain, teacher to student text to commentary, question to answer, in the tropical isolation of coastal Kerala. The world beyond those green hills did not know they existed, and they in turn did not know that Europe was slowly awakening to the Renaissance. They were alone with their mathematics, and that mathematics was about to become something the world had never seen. To understand what made the Kerala school revolutionary, you need to understand what mathematics looked like before Madhava. For thousands of years, mathematicians across every civilization had worked in the realm of the finite. You could calculate the area of a square, the circumference of a circle, the diagonal of a triangle. You could solve equations. Or you could count and measure and approximate, but there was a wall, and that wall was the infinite. Certain quantities, the ratio of a circle's circumference to its diameter, which we call pi, the sine of an angle, the arc of a curve, could not be expressed exactly using the arithmetic tools available. Mathematicians could approximate them, sometimes very cleverly, but they could not capture them, not truly. What Madhava did was to look at that wall and walk through it. He understood, and this is the staggering part, that certain quantities could be expressed as infinite sums, that if you kept adding smaller and smaller terms, following a specific rule, the sum would converge to an exact value, not an approximation. An exact value approached asymptotically in the limit. This is the fundamental insight of what we now call infinite series, and it is the conceptual doorstep of calculus. Consider what Madhava derived. He found a series expansion for the sine of an angle. Expressed in modern notation, he showed that the sine of x equals x minus x cubed over 3 factorial, plus x to the 5th power over 5 factorial, minus x to the 7th power over 7 factorial, and so on, continuing forever. This is the Maclaurin series for sine, a result that European mathematics would not formally establish until the work of Newton in the 17th century. Madhava had it in the 14th. He found the same kind of expansion for cosine. He found a remarkable series for the arctangent function, a result so important that it carries his name in some scholarly literature. The Madhava-Leibniz series. Expressed as the relationship between pi and an infinite alternating series, it states that pi divided by 4 equals 1 minus 1, third plus 1/5 minus 1/7, continuing forever. This precise formula was published in Europe by Leibniz in 1673. Madhava had derived it approximately 3 centuries earlier, but here is what makes Madhava's achievement even more extraordinary. He did not merely find these series, he understood their error. He derived correction terms, sophisticated adjustments that could dramatically improve the accuracy of a partial sum, allowing him to calculate values of pi correct to 11 decimal places. 11 decimal places in the 14th century, in a village on the banks of the Nila River, without a printing press, without algebraic notation as we know it, without any of the symbolic tools that we consider essential to mathematics today. How did he think? This is the question that haunts every historian who has studied the Kerala school. Madhava worked in Sanskrit verse, a tradition that encoded mathematical results in poetic form, in part for memorization, in part for the inherent beauty of the language. His results were expressed as verses that could be chanted. The mathematics lived in the music of the words. His successors would have to not only understand the results, but decode the linguistic structure that carried them. Nilakantha Somayaji, writing around 1500, went further still. In his masterwork, the Tantra Sangraha, Nilakantha revised the astronomical model of the solar system in a way that was structurally very close to what Tycho Brahe would propose in Europe decades later. A heliocentric arrangement for the planets, nested within a geocentric framework. Nilakantha's planetary model was, in the judgment of some historians of astronomy, more sophisticated than anything available in Europe at the time. And then came Jyesthadeva, who in the early 16th century wrote the Yuktibhasa, a text so astonishing that scholars today are still working to fully assess its significance. The Yuktibhasa is written not in Sanskrit, but in Malayalam, the vernacular language of Kerala, making it unusually accessible for its time. And what it contains is something that has no parallel in the medieval world. Proofs. Rigorous, much step-by-step justifications for the infinite series results of Madhava and his successors. using logic that closely resembles the formal reasoning of modern mathematical analysis. The Yukti contains arguments that look like the foundations of differential and integral calculus. Jyesthadeva discussed the summation of geometric series, the concept of the limit of a ratio as a small quantity approaches zero, and the accumulation of infinitely small quantities to find the area under a curve. He was not using the language of calculus, but he was doing something that, structurally, was astonishingly close to it. These men were thinking thoughts that the rest of the world would not think for 2 centuries, and they were doing so in total isolation, in a tradition carried quietly from teacher to student in the rain-soaked villages of southern India. Let us be precise here, because precision matters. This is not a story where we want to overclaim. The history of mathematics is too important, and the people in it too real, to be served by exaggeration. So let us look carefully at what the Kerala school actually achieved and what that means in the broader story of mathematical history. The central contributions of the Kerala school fall into several closely related areas. First, the infinite series expansions for trigonometric functions, sine, cosine, arctangent. These are not rough approximations or qualitative insights. They are mathematically rigorous results that can be verified in modern notation, that agree exactly with the results later derived by Newton, Gregory, Arneri, and Leibniz. They are the same results. Second, the Kerala scholars developed sophisticated techniques for working with what we would today call limits, the behavior of a mathematical expression as a variable approaches a specific value. The summation methods in the Yuktibhasa involve taking a large number of infinitely thin slices of a geometric figure and summing them to find an exact area. This is, in every conceptual respect, integration. The word does not appear. The formal definition does not appear. But the idea is there, breathing quietly in the Sanskrit text. Third, there is the matter of error terms and convergence rates, questions about how quickly an infinite series approaches its true value. Madhava's correction terms for his pi series are not heuristic guesses. They are derived quantities, arrived at through systematic mathematical reasoning. This level of sophistication is remarkable for any era. Now, Newton and Leibniz. This is where we must be especially careful. Isaac Newton, working in the 1660s, developed what he called the method of fluxions, a systematic framework for understanding how quantities change with respect to one another. He derived his own series expansions. He created the conceptual architecture of the derivative and the integral, and he proved the fundamental theorem of calculus, the deep result that differentiation and integration are inverse operations. This was genuinely new. This was a synthesis and a formalization that the Kerala school did not achieve. Gottfried Wilhelm Leibniz, independently and slightly later, developed his own version of calculus with a notation so elegant that it is still the notation we use today. His integral sign, his differential notation, these became the standard language through which calculus was communicated, extended, and applied across physics, engineering, and economics for the next 3 centuries. The Kerala school did not produce a formal calculus in this sense. They did not state or prove the fundamental theorem. They did not develop a general algebraic framework for differentiation. What they had were specific, extraordinarily powerful results. The series for sine and cosine and arctangent, the proto-integral summation methods, embedded within a tradition that was primarily astronomical and computational, rather than abstractly theoretical. So the question is not, did they invent calculus before Newton? When the honest answer to that question is no, not in the full sense. The question that does deserve a resounding yes is, did they discover key components of calculus, results that European mathematics would independently rediscover 2 centuries later through methods that involved genuine conceptual precursors to the limit, the infinite series, and the integral? And the answer to that is absolutely, demonstrably yes. There is a separate and more contested question. Did their work influence European mathematics? Did the results of Madhava and Nilakantha and Jyesthadeva somehow reach Newton or Leibniz? This question was taken up seriously by scholars beginning in the 1990s and early 2000s. Historians of mathematics, including George Gevorgis Joseph, and more recently Dennis Almeida and John Wallace's successors, may have investigated whether there could have been a transmission route. through the Jesuit missionaries who operated in Kerala in the 16th and 17th centuries, some of whom were involved in astronomical observation and who sent detailed reports back to Europe, through the spice trade routes that connected Kerala to the Persian Gulf and ultimately to the Mediterranean world, through Portuguese scholars who had sustained contact with Indian learned communities. The evidence for direct transmission is suggestive but not conclusive. There are tantalizing parallels, specific results appearing in European mathematics shortly after periods of intensified European contact with Kerala. But no smoking gun, no document that says explicitly, we found these series in an Indian text. And the scholarly consensus today is that the possibility of partial transmission cannot be ruled out, but it has not been proven. Newton and Leibniz are credited with independent discovery, and that credit stands on firm ground. What is not in doubt is the priority of the Kerala results. They came first, by centuries. So why didn't the world know? This is perhaps the most painful question in our story, because the mathematics was real, the insight was genuine. The proofs, insofar as the Kerala school produced them, were sound. These were not folktales or mystical intuitions. They were mathematical results of the highest order. So why, when the history of calculus is written, do the names Madhava and Nilakantha and Jyesthadeva appear, if they appear at all, only in footnotes? The answer involves a confluence of forces, is none of them fully satisfying, all of them historically comprehensible. The first is geography. Kerala was, in the 15th and 16th centuries, genuinely remote from the centers of European learning. The overland routes to India were long, dangerous, and intermittent. The sea routes around Africa, pioneered by Vasco da Gama in 1498, were new and primarily commercial in purpose. The Portuguese who arrived on Kerala's shores were interested in pepper and cinnamon, not in Sanskrit manuscripts on trigonometric series. The intellectual infrastructure for the transmission of mathematical ideas across that vast cultural and linguistic gulf simply did not exist in the way that it would exist for, say, astronomical data about planetary positions, which had practical value for navigation. The second is language, which the Kerala school wrote in Sanskrit and Malayalam. Sanskrit was accessible to learned Brahmins across India, but was virtually unknown in Europe. The great project of translating Sanskrit scientific texts into European languages did not begin in earnest until the late 18th and 19th centuries, by which point calculus had already been independently developed, formalized, extended, and applied to the entire landscape of natural philosophy. By the time scholars like Charles Wyche, a British civil servant working in Kerala, began publishing articles in the 1830s, drawing European attention to the Kerala mathematical tradition, the Newton-Leibniz framework had been the global standard for 150 years. The third is the form of the texts themselves. The Kerala mathematicians encoded their results in verse, a beautiful, efficient, and deeply Indian way of preserving knowledge in a culture where oral transmission was primary and paper was precious. But verse is opaque to outsiders. Understanding a mathematical result encoded in a Sanskrit verse requires not just Sanskrit literacy, but initiation into a specific hermeneutic tradition and understanding of the conventions by which mathematical content was linguistically disguised. Without a teacher who could explain the code, the manuscripts were effectively sealed. The fourth force is internal. The Kerala school was, in important ways, a closed tradition. Knowledge was transmitted within a specific community, the Nambudiri Brahmin scholars, and the institutional structures that might have disseminated it more widely within India itself were not well developed. Where there was no equivalent of the European university system, no international correspondence network of the kind that linked Newton, Leibniz, Huygens, Bernoulli, and their contemporaries in a web of shared discovery and competition. The Kerala mathematicians did not know each other's results in the way that European mathematicians of the 17th century shared and argued over each other's work. And then, after the 16th century, the tradition began to fade. The reasons are multiple and not fully understood. The disruptions caused by the arrival of Portuguese and later Dutch colonial power in Kerala. The decline of the patronage systems that had sustained scholarly communities. The gradual replacement of Sanskrit as the language of elite intellectual culture. Whatever the causes, By the 17th century, the extraordinary creative energy of the Kerala school had largely dissipated. The manuscripts remained. They sat in private collections, in temple libraries, in the hands of families who preserved them without fully understanding their significance. They gathered tropical humidity and the attention of insects. Some were lost entirely, and the world moved on, unaware that 2 centuries earlier, a man named Madhava had already walked through a door that the rest of humanity was still searching for. Here is what I want you to hold in your mind right now. We live in a world where the history of human knowledge is told as a single story, a story with a clear geography. Ancient Greece, then Rome, then the Islamic Golden Age preserving Greek texts, then the European Renaissance and Enlightenment, much then the scientific revolution, then modernity. It is a story that moves mostly west to east and then back west again, with India and China and the Islamic world appearing as way stations, as preservers and transmitters of the Greek tradition, rather than as independent sources of original discovery. The Kerala school breaks that story, not by replacing it, not by claiming that India deserves sole credit for calculus, but by demonstrating something more subtle and more important, that the story is incomplete, that independent lines of mathematical development were occurring simultaneously in places the story has not been paying attention to, that brilliance does not require a stage, a printing press, or a continental network of correspondence to be real. Charles Huish was the first European scholar to draw serious attention to the Kerala mathematical tradition. In 1832, he published a paper in the Transactions of the Royal Asiatic Society titled On the Hindu Quadrature of the Circle and the Infinite Series of the Proportion of the Circumference to the Diameter, exhibited in the 4 Shastras. It is a dry title for a thunderclap of a paper, which demonstrated clearly that Indian scholars had developed infinite series for pi and for trigonometric functions, and he identified specific Kerala texts, the Tantra Sangraha, the Yuktibhasa, that contained these results. The mathematical community of 1832 largely ignored him. This is not entirely surprising. The early 19th century was not a moment when European scholars were culturally prepared to believe that significant original mathematics had occurred in medieval India. The framework of Oriental scholarship at the time was deeply shaped by assumptions about European intellectual superiority. Huish's evidence was treated as a curiosity, a footnote, and then quietly set aside. It was not until the second half of the 20th century that the Kerala school began to receive sustained scholarly attention. The historian of mathematics C.T. Rajagopal and his collaborators published a series of important papers in the 1940s through 1970s that translated and analyzed Kerala mathematical texts with rigor, demonstrating in modern mathematical language precisely what had been achieved. Their work laid the foundation for the broader recognition that has followed. Today, the Kerala school is acknowledged in the historical literature. The Madhava series, the Yuktibhasa, the Tantra Sangraha, these are discussed in serious academic histories of mathematics. The question of possible transmission to Europe is actively debated by specialists. A small but growing number of popular science books have begun to include the Kerala school in their narratives of mathematical history. But walk into any secondary school in the world, open any standard textbook of calculus, ask any student who invented calculus. Newton, Leibniz, Madhava, who? And here is the deeper truth I want you to carry with you. The real story of the Kerala school is not primarily a story about credit. It is not a story whose point is to say, India deserves more glory in the history of mathematics. That framing, however understandable, is too small for what actually happened. The real story is about the structure of knowledge itself, about how ideas travel and how they don't, about the difference between a discovery and a discovery that changes the world, about the 1,000 contingent, fragile historical accidents that determine which ideas get taken up, extended, argued over, built upon, and eventually woven into the fabric of everything, and which ideas, equally brilliant, equally real, equally true, end up sleeping quietly in a manuscript on a shelf, waiting for someone to find them. Madhava's series for pi is not less beautiful because Newton found it again 200 years later without knowing it had already been found. The Yuktibhasa's proto-integral arguments are not less mathematically significant because Jyesthadeva had no students in Europe. The Kerala school's mathematics is exactly as profound as it is. What history failed to give it was not validity. What history failed to give it was connection. And connection, the web of correspondence, of translation, of argument and counterargument and collaboration, is what turns a discovery into a revolution. The Kerala school had the first without the second. Newton and Leibniz had both. And that, more than anything else, is why you learned one name and not the other. There is a phrase in the history of mathematics that I find quietly devastating. It is the phrase independent discovery. Independent discovery means that two people, in different times and different places, with no knowledge of each other, looked at the same mathematical reality and found the same truth. It happens more often than you might think. Newton and Leibniz with calculus, Bolyai and Lobachevsky with non-Euclidean geometry, Darwin and Wallace with natural selection. When independent discovery happens in the historical record, we celebrate it as evidence of the power of human reason, that the same territory of truth can be reached by different paths. And that is beautiful. But when one of those discoveries happened first and happened in a language and culture that the rest of the world couldn't read and sat in a manuscript for 5 centuries before being recognized, then independent discovery is also a word that covers a wound. A wound in the narrative, a place where the story of human knowledge has a gap. The Kerala School of Mathematics and Astronomy filled a gap that no one in Europe knew existed. They explored a mathematical landscape that the West would not reach for another 200 years, and they did it quietly, alone, by the light of oil lamps in villages no one has heard of, in verses written in a language no European could read. They were, for the purposes of global mathematical history, invisible. They are a little less invisible now, and that matters. It matters because Madhava of Sangamagrama was a genius, and genius deserves to be known. It matters because the Yuktibhasa is a document of extraordinary human intellectual achievement, and extraordinary achievements deserve to be read. It matters because every student who learns calculus is inheriting a tradition that is broader and older and more global than any single culture's story of it. It matters because the history of mathematics is not just a list of results. It is a story about how human beings in every corner of the earth, in every language, have been reaching toward the same truths. And when we tell that story fully, when we include the Kerala riverbank alongside the English country house and the Leipzig library, we are telling the truth about what mathematics actually is. Not a European invention, not an Indian invention, a human one. So the next time someone tells you the story of calculus, you know what to say. You know about a man named Madhava who stood on the edge of the infinite 800 years ago and looked in. You know about the Yuktibhasa, sitting in a manuscript, carrying proofs that the world wasn't ready to receive. You know that the story of human knowledge is larger, stranger, and more beautiful than any single telling of it. And now, so does anyone who watches this. If this story moved you, if it made you see mathematics differently or history differently, or the world a little differently, please subscribe to Numbers and Narratives by Blessright. Share this video with someone who needs to hear it. Leave a comment below telling me, what part of this story surprised you most? I read every single one. There are more stories like this one, stories of brilliance in places you weren't told to look. We are just getting started.